Yes, hello and welcome to my talk, Topology Concepts and the Deconstruction of Metalorganic Frameworks into their so-called underlying nets. Actually, this is a talk which I gave 2 weeks ago at this nice little workshop about structure and topology at the heart of MOF chemistry, which was organized by the Technical University of Munich and was held in the framework of the Priority Program COORNET of the German Research Foundation DFG, initiated by Professor Fischer. And now I decided to make a screencast of this talk to share this lecture with you, with those people who couldn't attend, and for everyone who is interested in that topic. Okay, let's begin. In the next 50 minutes or so, I will try to give you a brief overview of what is meant when framework chemists are talking about topology. And we will see how framework compounds can be turned into networks. So the outline is as follows. There are roughly 3 parts. First, I think it is not clear for everyone in which way topology on the one hand and graph theory on the other are connected, and what networks actually are. So I will say a few words about that and will introduce you to the basic terminology, the basic ideas. The second section is concerned with the question why we should actually consider metalorganic frameworks as networks. So what is the advantage of the network approach? And it will turn out that this is another way to classify crystal structures. And we will see, of course, a few examples how we derive at these nets the so-called deconstruction or simplification process. And finally, I will say something how 2 and 3 periodic nets, this means nets which are periodic in 2 or 3 dimensions, can be described or characterized. I will explain at which properties the software package ToposPro is looking at in order to distinguish between different nets. So, what are vertex symbols, point symbols, extended point symbols, what are coordination sequences, what is the difference between rings and cycles, and so on. And we will refer to the reticular chemistry structure resource, the so-called net center. Okay, let's begin with topology. If you have a look at Wikipedia or other encyclopedias, you will find roughly a definition like that. Topology, from Greek topos, place, and logos, study, is a fundamental subdiscipline of mathematics which is concerned with properties of mathematical structures in space, or you can also say objects in space, and this means a set of points, and now the important point, that do not change under continuous deformation. Okay, to give you an example, topologically viewed, a sphere is identical with a cube, is identical with an irregular blob like this. And a torus is identical with this object, which can finally continuously deform to such a coffee mug, as can be seen already here in this smooth animation. And a double torus can be continuously deformed into such 2-handled vase. This means we can also consider these objects of being composed of clay or rubber. All continuous deformations do not change their surface properties, no matter how the concrete shape looks like. So, to be topologically the same, certain operations on such objects are allowed, namely stretching, bending, twisting, crumpling, squeezing, distorting, and so on. But you probably already recognized what the fundamental difference is between, say, a sphere, a torus, and a double torus. Exactly, it is the number of holes in the surface. The number of holes in an object is a fundamental property of a surface, and in topology it is called the genus. We see here in this animation a discontinuous transformation between a torus and a sphere and back to a torus. So a body with genus 1 to a body with genus 0 back to a body with genus 1 again. And we see that this transformation is discontinuous. First, you have to cut the torus along its periphery, then you can deform this tube-like surface continuously, but in the end, you have to glue this surface together at the poles in order to obtain a complete or a closed sphere. In other words, these operations are not allowed. Gluing together parts that were previously unconnected, breaking up or tearing parts that were previously connected, or cutting holes into an object. Okay, now let's switch to the first time to a metal-organic framework compound, namely to this famous MIL53. Why is it famous? Because it comes in two flavors, so to say, in two states, because it can breathe. In its activated form, we have here these relatively large, one-dimensional rhombic channels running perpendicular to the drawing plane. It is orthorhombic and the space group is IMMA. But now, if we adsorb small molecules like water or CO2, then this MIL53 undergoes a dramatic phase transition to this narrow pore state. So the MOF breathes out. Although somehow opposed to human breathing, because this happens while molecules are inhaled, so to speak. But anyway, the unit cell considerably shrinks, and the extent of the volume change of the unit cell is, or at least was, unprecedented. Okay, during this phase transition, almost everything changed. The fractional coordinates, the symmetry, the space group, everything what is characteristic for a crystal structure. But do you really consider these two variants as fundamentally different? Well, from a topological point of view, they are identical. Why? Because they can be continuously transformed into each other. And here continuously means without breaking or reconnecting any bonds. And this is exactly the link, the relation to topology. The only difference between the examples before and this chemical object is that we have here not a continuous surface but concrete building units. Building units which can be identified as nodes or vertices and entities that connect these nodes. These are called the edges. And because there is a one-to-one relationship, a mapping, so to say, between the set of vertices and set of edges in the one and in the other state, they are topologically the same. Or to put it simpler, the connection scheme between the nodes is identical. And this means that we have two topologically identical graphs or nets. Okay, up to now you do not know what a graph is or what a net is, so what is a graph? A graph is again a mathematical object, an abstract object in which vertices are connected by edges. So a thing like that. What is important is that in a mathematical graph, these objects do not have real physical properties. The vertices are abstract, infinite small points that do not have a dimension, and the edges have also no properties, for instance a length, although here in this drawing, of course, they have a certain length. The only thing that matters from a mathematical point of view is whether two vertices are connected to each other or not. In principle, there are many different kinds of mathematical graphs. However, if we consider metal-organic frameworks as graphs, we are exclusively faced with networks. So what is a net? A net is only a special kind of graph which is connected. This means there is a continuous path from all vertices to every other vertices, which are periodic. So we have a unit cell which translates in 1, 2 or 3 directions in space. Furthermore, we have no so-called directed edges, so it does not matter if we have a link between this vertex and that vertex or the other way around. It is only important if two vertices are connected. We disregard from any multiple connections between vertices. There are no loose ends. And finally, nets have no loops. That is, vertices which are connected to themselves. And these last 4 properties qualify graphs as simple graphs. So, to summarize, a net is a graph which is connected, periodic, and simple. To illustrate this a little further, let's look at some graphs. This is a graph. It looks like a metro plan or a tube plan, but it is a non-simple graph because it has loose ends. This means vertices which have only one neighbor. This is also not a simple graph because it has loose ends and the red and dark blue train travels only in this direction and that direction, but not backwards. So this means we have directed edges, therefore a non-simple graph. This star-like ensemble, which looks like Orion, is a simple graph, however it is finite. And this would turn it into a non-simple graph because of this loop. Actually, in organic chemistry, graphs are used frequently. This is the graph of anthracene. But it is a non-simple graph because of these multiple bonds. But this would be a simple graph, the molecular graph of adamantane. But of course, it is finite, it is not periodic. This would be an example of a disconnected graph, or the topologist would say this is a disjoint graph being composed of two connected, simple subgraphs. Therefore, again, a non-simple graph. But this is an infinite, connected, simple, periodic net. Here we see the unit cell of this two-periodic net called HNA. And this is a fraction of the three-periodic net of diamond. So, okay, nets are only mathematical things, but our metal-organic frameworks are physical objects. They are, for instance, embedded into our 3D world. And this leads to two important questions. First, how should a network be presented to characterize its properties? And second, what properties do we actually have to explore or specify to be able to say that two nets are the same or not? First question. As I said, mathematically, a graph is only a certain set of vertices plus a certain set of edges, which specify which vertex is connected to which other vertex. But if we now want to assign these vertices coordinates to our 3D world, we can do this in different ways. Such an assignment is called an embedding or also realization. And when we do this, we speak then about nodes instead of vertices, and we speak about links instead of edges. And in this way, we linguistically distinguish between abstract graphs and concrete nets. So, and as I mentioned, this embedding can be done in different ways. Look, for instance, at these three variants of a uninodal three-coordinating net. All these variants can be transformed into each other without breaking or reconnecting links. Hence, they are isomorphic. But what is different is their symmetry. The one on the right has the lowest symmetry, 4 nodes per unit cell, but we can transform it into this one on the left, which has the highest symmetry. There are only 2 nodes per unit cell and the plane group is P6mm. And in chemical topology, one rule is exactly that. Place the vertices to such coordinates that you derive at nets with the highest possible symmetry. Second question. What we obviously have to answer is this question. Which types of vertices are connected to which other type of vertices? How many different vertices are there? How many edges? But what do we actually mean by different? So we are dealing with infinite extended networks. Another question could be, is perhaps the coordination geometry decisive? Well, in the first instance, not. Think about a tetrahedral and a square planar node. Topologically, they are absolutely identical. Because, again, they can be continuously transformed into each other. You can take a hammer and can squish this tetrahedron into this square. This means the geometry is strictly speaking not a property of a vertex. But if we now look at these two nets, which are composed of tetrahedral or square planar nodes, then we see, of course, these nets are different. The three-dimensional diamond and the two-periodic SQL net are very different. So the answer is yes, but we do not know why. It is very interesting. You can build up to approximately 230 different uninodal nets by putting together only 4 coordinating nodes. Okay, then perhaps it is sufficient to characterize the coordination number and the geometry of the vertices that build a net. This is also not the case. See, for instance, these two nets called SQL and NBO. In both nets, all vertices are coordinated in a square planar fashion, but the nets are clearly different. We see this, we recognize this immediately, but the question is, as stated before, how can we describe this in a more scientific and accurate way? In which way are they different? Okay, we will come back to this question, but first let's look how we turn our framework into networks. The first example is about zeolites, and the reason for this is because topology has a relatively long tradition in this field. The primary building unit of all tectosilicates are, of course, such silicon or aluminum oxygen 4 tetrahedra. The interesting thing about zeolites is that all zeolites are built exclusively from corner shell tetrahedra. And although this is valid for all zeolites, up to now approximately 230 different framework types are known. These different types are of course characterized by their rings and cages, which have different sizes. Here we see one of the typical secondary building units, such a double 4-ring abbreviated D4R. Okay, now if we want to turn these zeolites into nets, we do the following. The chemical nature of the tetrahedral coordinated atom does not matter. It is just a T atom or simply a node. Furthermore, as the oxygen atoms are not branching points, they can be omitted. And because we focus only on the covalent networks, the charges and counterions can also be disregarded. What is left then is only a periodic network of T nodes connected by links. Here shown again in its network-like representation with additional links to neighboring nodes. And we can take this as a first rule: a two-coordinating vertex is not a vertex but an edge. So in this network-like representation, zeolites look like that. We see here the sodalite, forgesite and the Linde type A zeolite. So now, how can we describe these nets? Well, one approach is to operate with zeolitic SBUs. The problem is that the SBUs are not unique. For instance, you can build all these 3 different zeolites from this type of SBU, from this regular hexagon. Of course, the construction principle or construction plan, how to assemble these hexagons, are different, but the SBU itself is identical. And related to this, the SBUs are not unique in an additional sense, namely we can choose different SBUs for the same type of zeolite. You can also build LTA from double 4-rings or octagons. And the same holds for the tertiary building units, the typical cages which occur in zeolites. They are also not unique and kind of arbitrary. Therefore, we should look for other, more accurate descriptors, and these are available. I will show you this later. The second example is concerned with some historical stuff from A.F. Wells, one of the main founders of the network approach in chemistry. Here we see the structure of strontium disilicide. From a structural point of view, this compound is rather unique. It builds its own structure type, and no other compound in the inorganic crystal structure database belongs to this type. To be of the same structure type, certain criteria have to be fulfilled. the compounds must belong to the same space group, the atoms must occupy the same Wyckoff positions, and the composition, or you can also say stoichiometry, must match. Also, categorizing this compound in terms of coordination polyhedra is not possible here. There are no such prototypical coordination polyhedra. Okay, another compound. This is the crystal structure of H2O2, hydrogen peroxide. We have covalent oxygen-oxygen and OH bonds, and there are additionally H bonds. It crystallizes in this tetragonal space group and again builds its own structure type in the inorganic crystal structure database, and again no other compound belongs to this structure type. Last example. This is the crystal structure of cesium diberyllium pentafluoride represented in the coordination polyhedra mode. This compound is not assigned a structure type at all. And we see the coordination polyhedra around the cesiums are not very regular. But now, three very different compounds. But what do these compounds have perhaps in common? Well, that the structure, or to be precise, that certain parts of the structure can be regarded as networks. Here, it is the network of the silicon atoms. They build a net which in the nomenclature of Wells is called the 10-3A network. In short, this means the silicon atoms build vertices which are 3 coordinating, and we have 10-membered rings. And this A is just another qualifier because there are other but different 10-3 nets. In H2O2 we have the covalent OO and OH bonds, and if we take 2/3 of the hydrogen bonds as additional edges, we have again a 10-3A net. And in this compound, well, these beryllium fluoride 4 tetrahedra are, analog to the zeolites, exclusively corner connected. So the fluorides can be omitted, and if we now connect the beryllium atoms, then we have again a 10-3A net with 3 coordinating beryllium atoms. And we already know that we should maximize the symmetry of the net, and in turn this gives in all 3 cases the same net with the same space group I4132. 10-3A is the name of Wells, and SRS set in bold is another name precisely from the reticular chemistry structure resource, in which each net is given a unique identifier, a unique 3-letter code. You see here not 3 coordinating vertices but such triangles. This is called an augmented representation. This is the reason why here is an additional extension, this -A. However, this A has nothing to do with this A from Wells. This A stands for augmentation, and augmentation means the following. In an augmented version of a net, each node is replaced by its so-called vertex figure, and this means the coordination polygons or polyhedra. Here in this example, the BCU net, each node is surrounded by 8 neighboring vertices in form of a cube, so we replace now each vertex with a cube. And the advantage is, of course, that it is much easier to infer the coordination environment and its orientation in space. What should be also clear is if we put additional nodes into the parent net to derive the net in its augmented version, then we will have, of course, a different net. In this case, it is the uninodal 4-coordinating net PCB, which stands for polycubane. Okay, but let's stay a little on this network approach. There are several ways to categorize solid-state matter or crystalline structures, in particular inorganic crystalline compounds. There is this symmetry aspect, expressed as belonging to the one or other space group. Many structures can be considered as being derived from sphere packings. Others are best described by coordination polyhedra. And then there are these prototypical structure types. But we just saw examples in which none of these concepts were really convincing. And here the network approach might be useful. Wells described the advantage of the network approach as follows. An advantage of describing such frameworks as systems of polygons, and these are the rings, rather than as sets of points generated by groups of symmetry operations is that a number of substances may have essentially the same structure, but can be distorted in different ways so as to have, for example, tetragonal, orthorhombic or monoclinic symmetry, for instance for these three compounds, platinum sulfide, palladium oxide and copper oxide. And it goes further, provided that the system of linked polygons is the same, then all three structures are described as based on the same three-dimensional net. And in this sense, these nets have a deeper structural significance than space groups. We can summarize this as the network approach is a reasonable and additional way of categorizing solid-state crystalline structures. And this statement is in particular valid for framework compounds with directed and strong bonds. Yeah, and this is of course exactly the reason why the network approach was reinvented or rediscovered by the Metalorganic framework community. So let's look how Metalorganic frameworks are turned into their underlying nets. In general, they are relatively easy to deconstruct, although not as easy as zeolites. All you have to do is to identify the metal or metal oxide cluster, this SPU, or to be precise, the border between this cluster and the linker. And what we also should do is to take any additional branching points of the linkers into account. There are some cases in which ambiguities remain. This is particularly true for metalorganic frameworks with rod-like SPUs, but as I said, in general it is not a difficult task. And to keep it simple, let's look at this prototypical MOF 5, which you can see here at three different levels of abstraction. We can zoom in a little bit and then we see that the SPU is composed of one zinc 4 oxygen tetrahedron, and a tetrahedron of course has 6 edges and these edges are bridged by 6 carboxylates. And now you have to look where this SPU extends into the linker. And these are the so-called points of extension. And these are the carbon carboxylate atoms. And if we now connect these points of extension, then we get this overall shape of the SPU, obviously an octahedron with 6 connection points. And the linker is the terephthalic acid dianion. It connects exactly 2 SPUs and is therefore only an edge. So, and if we now replace this SPU by a node at its center of mass and connect these nodes according to the connection scheme, and this is exactly what ToposPro does, then we will end up with this net. Octahedral 6 coordinating nodes bridged by edges. All nodes are symmetry related to each other, and this means that we have only one node. Hence, the net is a uninodal net. Only one type of vertex is present. And this net is known as the PCU net. Again, this is the unique 3-letter code from the RCSR. If we now use the same ingredients for the SPU, and we use only ditopic linkers, no matter how it exactly looks like, it can be shorter or longer, it can be mono or polycyclic in the aromatic backbone, it can have additional side groups, then it is very likely that we obtain an identical net. And the realization and rationalization of this finding led to the reticular chemistry concept, and in the first instance to these famous isoreticular metal organic frameworks, these MOFs. Omayagi defines reticular chemistry as stitching molecular building blocks into extended structures by strong bonds. By the way, I can recommend this lecture by Omayagi given in the last summer, which is available on YouTube. There he speaks about the very beginning of metal organic frameworks, not only MOF5 but also MOF2 or MOF3, which are not so famous compared to MOF5, but he also speaks about the latest development of metal organic frameworks, for instance, how MOFs can be used for water harvesting in arid regions, in deserts. Okay, this reticular chemistry concept was and still is amazingly successful. More and more and more complex nets have been designed or realized, and also nets which were previously unknown, nets with new topologies. And this is always a thrilling moment in the life of a framework chemist. If you have a net which nobody has seen before, and you made it out of chemistry, I think that's always amazing. Okay, perhaps one more example about simplification of MOFs, MOF 505. MOF 505 is made up of these famous copper paddle wheel motifs. So we have a square planar SBU. The linker is biphenyl tetracarboxylate, and here the question arises if this linker should be considered also as a tetratopic linker, which is in its symmetry maximized form also a square planar node. It is not forbidden, and we can do this, and then we would end up with a 4-coordinating net called NBO. But what are perhaps other possibilities? Yes, exactly. We can consider the linker as being composed of two triangles. This is a branching point, and this is also a branching point. And if we do this, then we derive at a binodal 3-4 coordinating net called FOF. Here both possibilities are shown again, both in its augmented version. As I said, it is not forbidden to take the linker as a tetratopic linker, but there are at least 3 reasons why we should consider the linker as two triangles and not as a square planar node. First, in particular, if you make the linker longer and longer, it is obvious or evident that a square planar representation is simply geometrically not appropriate. Second, also from a topological point of view, it is recommended to use the two triangle version because otherwise too much information will be lost. Note, for instance, that in the NBO net version, the linker is identical with the SBU. And third, MOF 505 crystallizes in a space group belonging to the trigonal crystal system, but the net NBO is cubic, and I think this is likewise not appropriate. Okay, but of course, as I said, it is not forbidden to take the linker as a square planar node, and that means topology can also be a very subjective field. Now we know how to deconstruct metal organic frameworks, and we saw different names for specific nets, but these are only names for them. We still have to see how a network can be characterized and how we distinguish between different nets. So we can ask, is there perhaps something like a unique signature for a net? And the answer is yes. We can evaluate a unique signature with 2 software packages, however, both work very differently. The first is called Systre, which stands for Symmetry, Structure Recognition and Refinement. It was invented by Olaf Delgado Friedrichs, a German mathematician now living in Australia. And this program is able to answer the question if two nets are the same or not. There are highly mathematical algorithms involved. It works with complicated things called labeled quotient graph and so on. But in the end, it generates a unique Systre key, so a key which is characteristic for a net. I know roughly how this program works, but do not expect that I can answer any detailed questions about that. And then there is ToposPro. Here you see the two programmers who made this tool available, Vladislav Blatov and Alexandre Shevchenko, from Samara in Russia. And there is a third researcher involved. This is Davide Proserpio from Milano, who is working partly also in Samara. And by the way, in my opinion, all four of them are really genius people. ToposPro evaluates three characteristics of a net, namely the vertex symbol, the point or extended point symbol, and the so-called coordination sequence of all vertices of a net. And these three properties together have been proven to be unique or almost unique. And the classifying is done with a database in the background, which then says, well, this signature is the signature of the NBO or PCU or SQLnet and so on. So let's get familiar with these vertex symbols, and we can do this together. Here you see a first example, a two-periodic net named CEM. It is a unionodal, 5-coordinating net, so once again only one different kind of vertex is present. Now here is the recipe in order to obtain the vertex symbol for such a two-periodic net. We have to look at each vertex and have to specify the size of the shortest ring in which each angle, this means pair of edges, is involved. And we do this in cyclic order, meaning that we follow a steady direction, either clock or counterclockwise, and that we order the polygons according to increasing sizes. So ABC, the increasing sizes, and we put a dot between every ring size. If polygons of the same size appear directly consecutively, then they can be grouped with the help of a superscript index, so like shown here. Okay, now let's turn to this net, and we take, for instance, this vertex shown here in blue. So what is the vertex symbol of this blue node? Yes, it is 3, 3, 3, 4, 4, which can be written also in this manner. This was easy. But sometimes the cyclic order is decisive. So look at this beautiful TTS net. So what is the vertex symbol here? Yes, it is 3, 3, 4, 3, 4. In this case, we have to carefully choose the direction. We should begin with the shortest cycle, but this can be this ring or that ring or that ring. And if we choose this here, the symbol would be 3, 4, 3, 3, 4. But then the numbers 3 and 4 are at the first and second rank. So we can take another rule. A highest number of small numbers should appear at the beginning. Now let's turn to 3 periodic nets. There are two interesting differences between 2 and 3 periodic nets. First, in 2 periodic nets, each angle is involved in only one shortest cycle or ring. In 3 periodic nets, it is possible that one angle is part of more than one shortest cycle or ring. This can be seen already here in this diamond net. If you look at this gray-red angle here, then we see that there are two shortest rings. So this is a 6-membered ring, and this is also a 6-membered ring. The general notation is given as shown here, so the number of rings are given as subscripts. This means there are n number of A rings at the first angle, m number of B rings at the second angle, and so on. The next thing is that we have to consider how the angles and hence the cycles or rings are sorted. In 3 periodic nets, this is dependent on the coordination number. In general, the number of angles for an n-coordinated node is n times n minus 1 divided by 2. For a 3-coordinating node, we have only 3 angles, and here we have to sort according to increasing ring sizes. This is simple. However, for a 4-coordinating node, we already have 6 angles, and for 4-coordinating nodes, there is a new rule. We should build group of pairs of opposite angles, and these are those that do not share a common edge. And then we have again to order from small to high numbers. So this means that we first have to look, for instance, at this orange and red pair, then at these 2 blue pairs, and finally these 2 green pairs. We can do this now for the well-known diamond net. If you look at this black node, then we see there are 2 6-membered rings for the red and also for the orange pair of edges. This is also the case for both blue angles and also for these 2 green pairs, 6, 2, 6, 2 again. This means that altogether not less than 12 6 rings meet at each vertex. For higher coordinated nodes, there is no simple sorting rule anymore. And the rule here can be summarized as small numbers first, this means small ring sizes, and also small number of occurrences of rings, that is, small subscripts should come first. And now the question is the vertex symbol sufficient to characterize a net? Unfortunately, this is not the case. There are a few nets for which the vertex symbol is identical. This means that the vertex symbol alone is not sufficient in order to discriminate between different nets. This is the case, for instance, for these 2 nets, diamond and Zeolite. But what is different is the coordination sequence. What is the coordination sequence? It is given as a series of numbers in which these numbers specify the number of vertices that are exactly 1 edge away from the reference vertex. So these 4 blue nodes, 2 edges away, this means these 8 green nodes, and so on. So for the 2 periodic net SQL, we see the sequence begins with 4, 8, 12, and so forth. So let's look now at the coordination sequences of diamond and Zeolite. Interestingly, they are the same for the first 2 coordination shells, but from the 3rd on, they are different, and the difference is increasing. If you look up for a net in a database, then usually also this cumulated 10 value is given, and this is just the sum from the 1st up to the 10th shell plus the 1 reference vertex. You might now ask, perhaps the coordination sequence is unique. But this is likewise not the case. Look at these 2 zeolites, or the nets of these zeolites, LTA and rho. They have absolute identical coordination sequences, at least up to the 10th shell. However, here the vertex symbol is different. And this can be generalized. The combination of the vertex symbol and the coordination sequence is at least almost unique. And this together is taken as an identifier. Maybe a last point. Some authors use point symbols instead of vertex symbols. So what is the difference? In vertex symbols, the shortest rings of angles are specified and the number of such rings are specified too. And these angles are never grouped. Every angle is separated by a dot. In point symbols, you look for shortest cycles instead, and you only specify the size of one shortest cycle, no matter if there are perhaps two or more such shortest cycles in one angle involved. So only n cycles are specified. This is one difference, and the second difference is that cycle sizes instead of ring sizes are specified. So what is a ring and what is a cycle? A cycle, which is also called a circuit, is a continuous closed path of any length in which the start and end vertex are identical. A ring, in contrast, is also a cycle, but a special cycle, namely a cycle which is not the sum of two smaller cycles. This is the mathematical definition, and there is another description which is much easier to grasp. A ring is a cycle without a shortcut to the home vertex. An example will clarify this. This is the net fxt. Although it looks not like a uninodal net, it is indeed again a uninodal net, precisely with 3 coordinating nodes. But all nodes are symmetry related to each other, so we have to specify only one vertex. We can take this one here, for instance, so let's specify its vertex symbol. We have a 4 ring for the angle AB, a 6 ring for the angle BC, and a 12 ring for the angle AC. Now the point symbol. Again, we have a 4 cycle for the angle AB and a 6 cycle for BC, but for this last angle AC we can go along this way. And this is only an 8 cycle. And here is the potential shortcut. Along this path there is a vertex from which you would reach the home vertex by just one edge, and this is called a potential shortcut. We can also say the 8 cycle is the sum of the 4 and the 6 cycle, hence it is not a ring. The reason why some authors use point symbols instead of vertex symbols is that they can be written in a much more compact manner. However, it is not recommended to use point symbols, and this can be demonstrated with this example. There are comparable many nets which have the same point symbol. This is the case, for instance, for SRS and THS. Wells, of course, recognized that these nets are different, so he decided to use additional alphabetical postfixes, and we see that the vertex symbol is different. So we can conclude that point symbols are not sufficient to characterize networks. Maybe a very last thing, there are some nets for which certain angles of a vertex are not involved in rings at all, because all shortest closed paths are only cycles but not rings. This is already the case for the relative simple net PCU. The cis angles are all involved in 4 rings, no problem. But what about these trans angles? All shortest ways back to this orange home vertex have shortcuts. And then this is marked with an asterisk in the vertex symbol. If this is the case, one can specify the point symbol instead, or even better, the so-called extended point symbol. Here, not only the one shortest cycle is specified, but also how many there are, how often they occur. So for this transangle, we can go also along this shortest cycle, and also along this path, and also along that path. So there are 4 shortest cycles for each of the transangles. Here the vertex symbol, the point symbol, and the extended point symbol for the net PCU is shown again in this overview, and I think this was it. Perhaps this was a kind of a dip into the cold water of the ocean of topology. In Germany we say ein Sprung ins kalte Wasser, but I'm happy to answer your questions if I can. Thank you very much and see you.